In this video, we're going to learn about molecular geometry and something called VSEPR, or valence shell electron pair repulsion. So on the outside of atoms, you have electrons that exist. And the electrons can exist in either bonds when we're talking about covalent molecules or unshared pairs. But all of those things carry negative charges, right? So they're negative. They're going to push each other away, repel each other, so that these things that are on the outside of the atom spread out as far as they can possibly be from each other. And that results in the shapes that molecules form, which has long-term effects on what kind of polarity they have and how they interact in the world, boiling points, melting points, surface tension, all that stuff. And it has to do with their shapes first. So the first shape I'm going to go over is linear. This looks linear, right? This is what forms when you have two atoms bonded to a central atom and no unshared pairs. Okay, so what you end up with is a 180-degree bond angle, because that's as far apart as two things can possibly be from each other around a central point. Now, there is another type of linear molecule that you can have. So this, two atoms off the central atom. You can also have a linear molecule with just, anytime you have two atoms connected and nothing else, you're going to have a linear molecule, because anytime you connect 2 points, you get a line segment, which is a linear shape. The second shape I'm going to go over with you guys is trigonal planar. So this one is pretty simple as well. If you picture three things sticking off of a central point and spreading out as far apart as they can, you're going to end up with 120-degree bond angles. We're going to call this a trigonal planar geometry. Okay, so there's three things, so trigonal, and it's in the same plane. Now, when we get past those two, it starts to get a little bit more complicated, because the other shapes we're going to learn about contain unshared pairs, or in 3 dimensions, they don't form exactly the same as they would in 2 dimensions. So the first one I'm going to show you that's kind of not what you would expect just looking at a 2-dimensional model would be tetrahedral. Anytime you have 4 atoms bonded to a central atom, which carbon does all the time, you end up with them spreading out to be 109.5 degrees apart. That's a little bit different than when you expect. I mean, you think 4 things sticking off the middle in 2 dimensions, that results in 90 degrees. But in reality, the way it all spreads out is about 109.5 degrees. So this would be a tetrahedral shape. And the bond angle is 109.5. 4 atoms bonded, no unshared pairs. Now, if I get rid of one of those atoms there, and I replace them with an unshared pair, you end up with approximately the same bond angle. Because, well, while this isn't in a bond, it is also going to repel the other bonding electrons equally, so actually a little bit more. So it's going to compress them together so that they don't form that trigonal planar shape. The reality is that it doesn't actually form a 109.5 degree bond angle. What you end up with is a little bit less than that, because while these electrons in the bond are stretched out between the 2 nuclei of the atoms in the bond, this unshared pair sits a lot flatter and kind of crowds in a little bit more, compressing everything else closer together. In reality, something with this shape, which would be called trigonal pyramidal, what you would have is probably something closer to a 107.8 or 107.3 bond angle, depending on what the atoms bonded are. So that would be a trigonal pyramidal shape, but if you're looking only at the electrons, it's just like the one we looked at before this. It's like a tetrahedral shape when you're looking at electrons only. However, when you look at the actual where the atoms are, you get a trigonal pyramidal shape. The next shape that we're going to have is going to be bent. Now, bents can come in one of 2 forms. This bent molecule has 2 atoms off the central atom with only 1 unshared pair. And based on its electron arrangement, you would say that that would be trigonal planar, right? Because you got 3 things sticking off a central point. But if you're only looking at the atoms, it forms a bent shape. And in reality, while it says the bond angle would be 120 here, realistically, because these sit a little bit flatter, you're going to end up with a slight compression of these bonds so that they get a little bit less than that, probably closer to 119, 118. Now, molecules can also be bent when they have 2 unshared pairs and 2 atoms bonded off of them. This results, if you're looking at all the electrons, it's just like the tetrahedral shape. You have 4 things sticking off, and they're going to repel each other the same way, and you have the 2 atoms bonded. So electron-wise, you would say this is tetrahedral, but actually the molecule's shape would be bent. And in reality, just like we've talked about before, the unshared pairs will compress everything else a little bit more. So instead of being 109.5, like water, for example, has this shape where you have two unshared pairs on the oxygen and the two hydrogens bonded, you have a 104.5 bond angle. You can see there's a decent amount of compression that results because of these unshared pairs. So today we've learned about 5 shapes. We've learned about linear, we've learned about trigonal planar, we've learned about tetrahedral, and then molecules that have the same electron geometry as tetrahedral in bent and the trigonal pyramidal. And we also learned that bent shapes can also result from a trigonal planar geometry with basically replacing one atom with an unshared pair of electrons.